Yeah, that's right. Actually, let me look a little differently. Okay, getting a little better confused. Screen start to short delay there. I'm going to go over what I did in the support course quickly to inspire you maybe to go back and look at that video if you find it useful. So you want to see what's in it. Now, there's some terminology and so forth about exponential functions that you won't be totally familiar with. So I'm going to explain it a little bit. So we've got f of x is 40 times 1.23 to the x. Now, you could compare that with like 40 times 2 to the x, couldn't you? 2 to the x has a graph that you understand, and you can vertically stretch it by factor 40 and just change your labeling of the y-axis, and you get a perfectly good graph of 40 times 2 to the x. Okay? Now, what's bigger, 2 to the x or 1.23 to the x? Well, you've seen the graph of 2 to the x and the graph of 3 to the x with that some detail. Okay? And I even squeeze the graph of e to the x in the middle there somewhere. The graph of 1.23 to the x, or 40 times 1.23 to the x, looks exactly like the graph of the exponential function that you constructed. Okay? It's just that the scale of the graph, the x scale and the y scale, are going to be a little different. We want to be sure we understand that. That every exponential function has the same shape, or the shape you get, I mean, there it is, or the shape you get if you flip it around the y-axis, so it's a decreasing exponential. And you saw both if you did the homework for today. Not everybody did. We got a test this week, so I'll transfer that for full credit off the beginning. Okay. How many of you taken the test? Okay. Yeah, I think you were in there yesterday when I picked up work. Okay. I haven't picked that one up yet. You want to know how you did it ask me after class. Okay. And I just give you no, yeah. I don't have a score, but I tell you what you bring. Okay. And then I give you more detail if you have when I have a chance to see what I don't. Okay, anyhow, what are the growth factor and the growth rate? Okay, so what do we mean by growth factor or growth rate and initial value? Now we talked a little bit before about compound interest, didn't we? Like if you got 5% interest, multiply by 1.05. Did we do that in here? Pretty sure we did. Well, this is like 23% interest. That makes sense? Okay. Well, the 23% is what we call the growth rate. You know, if you invest your money at 3%, you don't do as well as if you invested at 5%, assuming it's a safe investment. Does that make sense? Okay, you have a higher growth rate if it's 5% than if it's 3%. It grows a lot faster. This is growth rate of 23%. So this probably isn't interesting. You're not going to find a safe investment with a 23% growth rate or 23%. Okay, but that's what we mean by growth rate. So when I posed this quiz to the support course, we had an assignment where there were some problems that involve growth rate and growth factor. And incidentally, if you did that assignment, only one person did, so nobody's really get ready for the test or whatever. The fifth problem asks you, what's the growth rate or growth factor? They're different. Nobody would know how to answer that question. So, yeah, I like looking at people that answer and get full credit because the answers all make sense because it was the biggest question. Okay. Now, the point of that is you got growth factor. Growth factor is what you multiply. Factor is something that's multiplied by everything else. Okay. So what's multiplied by everything? Well, 1.23. That's a factor. So that's your growth factor. So you got growth rate 23% or 0.23, growth factor 1.23. Every exponential function has a growth rate and a growth factor that help you understand how it behaves. All right. And then what's the initial value? Well, that's really easy to see what that means. Okay, so, and then I said sketch a graph of the exponential shape in a rectangle. Didn't say label it because I could have said sketch an unlabeled graph. But when I say sketch the exponential shape, I just mean sketch the shape. Construct a shape like this. And then later we put numbers. Okay. All right. Well, so anyhow, and people actually did pretty well with this. I think most of the class got the growth factor, the 23% or 0.23, growth rate, 23% or the 0.23. And the growth factor was 1.23. And that's the factor that makes the thing grow. Now, the bigger your growth rate, the bigger this number, and the faster it's going to grow. Does that make sense? Okay. Now, the initial value is just the value of t equals 0. So if t equals 0, well, this is x equals 0, but we use t a lot with exponential functions because a lot of times models are functions of time. Okay. So we can use x or t kind of interchangeably. I said, okay, f of x. And I said if t equals 0, which must be right. I'll say that x equals 0, f of x equals f of 0, which is 40 times 1.23 to the 0, and 1.2 to the 0 is 1, so that's 40, right? Take a look at this to the initial value. Now, what's that say about the graph? Well, you go ahead and draw the graph. And you put an x and a y axis on it. And then, exactly, there's my function, but I don't know what numbers to use for my x values or my y values. Well, actually, you do know what numbers to use for your y values because you put the y axis here. Now, when x equals 0, there's your 40, right? When x equals 0, y has to equal 40. So there's your line y equals 40. Can you see that? I had to write it pretty small. Okay. So now that we know y equals 40, well, then we know this is 80, and this is 160, and down here's 20, and here's 20. Right? So we know what those numbers are because we know how this has been subdivided. I explained that in the support class. But I don't think you need the explanation. And if you do, you go back and read that explanation how you construct the graph. Everybody, I think, knows that. Okay, now, one thing we can notice about this graph is that every time we move over one, we move up one, and when we move up one, we move from a line to a line that's twice as high, don't we? Because each of these lines, we start here, we go halfway to 0, which is here. Then we go halfway to 0, which is here, halfway to 0. And we know that with the scale for the y. So we can be secure with that. We don't know what the x scale is for this function. Okay. How long is it going to take this function to double? Because every time you move over one of these lines, you double. Now, over here, here. If you know how long it takes to double, which is going to turn out to be about 3.4, okay, then you know how to scale the graph, and you can draw a graph that gives you good information. Okay, and you can also, of course, analyze the function. But you learn more by looking at the graph and thinking about it as far as the way the function behaves than you do by plugging numbers into the function. So, okay. Now, it's not completely true. There's a lot that we can do to analyze it, but most of that comes from calculus. Like there's a picture. The picture is very important. I use the example now. Let's say this is compound interest. You know, can get some kind of interest. But let's say that this is a fish pond. It's the example I used there. I said, okay, fish pond. When x is 0 or t equals 0, you have 40 fish. Okay. Now, there's a 23% growth rate. That means, let's say every month, so x is measured in months. Every month, you get 23% more fish. So you've got 40 fish. 23% of 40 is how much? Well, it's close to 10. Okay, because 25% of 40 would be 10 or 4. It's actually going to be like 9.2. Is that right? 40. I think it would be higher than 9.2, but keep that 9.2. Okay. First year, get 9 more fish. You have about 29, about 49 fish. Next year, well, 49 is almost 50, 23% of 50 would be like 12 more fish. Okay. So you're going to get more additional fish every year because you have more fish to take the 23% of. All right. Figure out how long this thing takes to double. Well, if you raise this to the, if x equals 2, you're going to have 1.23 squared, which is pretty close to 1.5. Okay. And then you multiply that by 1.23 and multiply that by 1.23 again, you get over 2. So 1.23 to the 4th power is more than 2. 1.23 to the 3rd power is less than 2. Knowing that, because I can do those calculations fairly accurately, I estimated that this thing would double in 3.4 months. Now, there's a way to calculate it. Divide the log of 2 by the log of 1.23. We'll see these rules in the chapter by the end of next week. I think you'll have these rules. Okay, and they're simple rules. They're easier than figuring out how to graph rational functions and polynomials, for example. Okay, does it make sense? So this is a simple way to calculate the doubling time, and then this is the time it takes to double. So that means that if this is the y-axis where x equals 0, then x equals 3.4 from this construction line. Because between this construction line and this one, we double. And then between this one and this one, we double again. So there's another 3.4, which makes 6.8. Now we've got a scale in this graph. And if this is a fish pond, we don't know for sure how the fish are going to, population is going to go. We think it's going to be a 23% growth rate. It might only be 18%, it might be 28%. Okay. So this graph is kind of a best guess. And this graph is just as good as that function, if you know how to read it. So let's say I'm trying to plan how much fish food to have. It's going to help if I know how many fish I'm going to have after 5 months. Where's 5? 5 months in this graph is on the x-axis between 3.4 and 6.8, a little less than halfway between this and this. So I'm going to draw my x equals 5 line here, and then I'm going to estimate my y value. Now, here's 40, so here's 80, here's 160, I estimated about 110. I thought, well, you can put 5 in for x and calculate this and calculate. Okay. I think you're gonna get some kind of close to 110. It might only be 100, it might be 120. But my graph is fairly carefully drawn, and that looks like more than one. Okay. Now, hopefully that makes some kind of sense. Another thing that we did that's also very important, understanding this function. And again, something that would be beneficial to you to work through if you don't totally understand it. Started with 2 points on a graph. Okay. And then I asked people to tell me a number between 5 and 10. Now it's going to be value of t here. This is a graph of population p versus time t. Populations in number of critics or whatever. Time t is in months. All right. So people chose 6. Actually, I kind of chose 7, but I actually don't. Okay, so it's 6. And then if this is 6 here, then t for this point would be 2. Okay. And we didn't say anything about t equals 4. We said, okay, population here. People kind of chose 70. Okay. And then what's the population here? If that's 70, that looks like maybe 25. This makes sense. So now we have an exponential function where the value is 70 when t equals 2. I'm sorry, value is 70 when t equals 6. Value is 25 when t equals 2. Here's our information. T equals 25, t equals 2, t equals 70, t equals 6. Form of an exponential function is a times b to the t. That's one form. There are other forms. Let's see, a times 2 to the kt. A times b to the kt. You're going to see all those forms, and they're easily related to this one. This is the easiest one to deal with right now. Okay. It's a times b to the t, because what we had before. That other function was 40 times 1.23 to the t, right? So like a would have been 40, and b would have been 1.23, and raised to the 2 power. Now this is going to be different. It's in the form a times b to the t, so what do we do? Well, if you have 2 points on the graph, you can get a straight line through it. You should be able to, but not everybody does. We got a couple of weeks ago. So you could get the equation of a straight line through this function. It wouldn't curve like an exponential function, and it wouldn't act like a population. Okay. So now we want to find an exponential function. Now, if you got a curve between, if you've got a straight line between 2 points, you can use y equals mx plus b form, plug in x and y to get an equation, plug in another x and y to get another equation. Then you have 2 simultaneous equations that you can solve by elimination. Okay. If you haven't taken the test, make sure you know how to do that. It's probably going to be on. So here we have a different form. It's not mx plus b, it's a times b to the t. What do? We take t to p. T equals 2, t equals 25, and we get 25 for p, 2 for t, 25 equals a times b to the second. I think everybody understands that. And then we plug this information in, we get this. Now we've got 2 simultaneous equations. How do we solve them? Well, I think one of your assignments use substitution a little bit. If not, then here's the method. Okay. I said solve the first equation. Solve 1, which means the first equation here is covered with circle 1. Solve this for a. Well, here's the equation. You want to solve it for a, you're going to divide both sides by b squared, aren't you? And hopefully that would occur to you instantly. if you're not solving these in your homework by showing all the steps, it's going to be less likely to occur to you than see here. So I keep urging you to write your steps out and keep reinforcing the operations that you use to solve problems. Okay. So anyhow, we have that. So here it is. Here it is. 25 equals a times b squared. What do? We divide both sides by b squared. So b squared here divides b squared here and leaves us a, and we get a equals 25 over b squared. Which, when you see this, you probably pretty quickly understand, yeah, that's going to be 25 over b squared. If not, be sure you're writing it out very carefully. Okay, now we take that, we get a equals 25 over b squared. What do we do with that? We put it in this side. So 25 over b squared replaces this a, and we get 70 equals 25 over b squared times b to the 6th. Right there it is. Now, people have a little trouble with the rules of exponents, and this is something you really want to be sure that you understand, because you're going to use it, especially in this chapter. Okay? And you don't want to be stumbling over the rules of exponents. Make sure you review them, because almost everybody is pretty fuzzy on the laws of exponents. How do you simplify this? Well, you divide the b squared into the b to the 6th. What do you get? You get b cubed, or you get b to the 4th. What power b do you think you get? By b squared into b to the 6th. Well, okay. Good to see your opinion. You guys didn't get worried about you. Okay. I only saw 3 fingers, but I thought your pinky was also attached to it. Okay. Make sense? Okay. So now the equation becomes 25 b to the 4th equals 70. How do you solve that? Okay. Well, first you divide by the 25, you get b to the 4th equals 70 over 25. And then what do? Well, it turns out you take the 1/4 power of both sides, and you get b equals 70 over 25 to the 1/4 power, which I estimated would be 1.18, because I was treating 70 over 25 like 1.872. Well, like actually more like 2 instead of 2.8. I don't know what wrong in my head, but something did. That should have been closer to 1.3. Okay. Well, now we know P is A times 1.18 to the T. Got the second, you go back into the first equation and replace B by 1.18. Should have been 1.3. Okay, but let's follow with the numbers I have here. Then I'll show you where I discovered that I've done something really ignorant to be able to find what it was. Well, that's easy to solve for A, isn't it? Just divide both sides by 1.18 squared and write it out to reinforce that you just did it, because it looks a little weird. Okay. There you have it. And 1.18 squared, I said it's about 1.394, and I think that's right. It turns out I was debating between 1.18 and 1.19. I was debating between 2 things a little wrong, but there it is. And if you divide 25 by this, you get 17.6, and there's your A. Well, now we have the form AB to the T. B equals AB to the T, and we just solve for A, and we solve for B. Which tells us now that P being equal to AB to the T with A equal 17.6, B equals 1.18 is 17.6 times 1.18 to the T. Then we check. Okay, well, another thing I ask people to do with the graph Or over to C. Said, let's estimate what P ought to be when T equals 4. Well, everybody knows how to do that. Everybody did a good job at that. Matter of fact, everybody in the class, only 3 people, but everybody in the class had the same estimate. They thought it was 45. Okay. Well, that looks pretty good to me. So I took 45 as the estimate. Then I came back and took my function and see, okay, if T equals 4, I should get about 45, right? Well, I plug in T equals 4. There it is. Okay, I got 35. That's way off 45. Clearly, when T equals 4, this curve is much closer to 45 than it is to 35. 35 is way too close to 25. Okay. Also, T equals 4 ought to be halfway between 2 and 6. Maybe that estimate's a little skewed. But in any case, even if T equals 4 is a little further over that, the estimate's going to be even higher. We're not going to get 35, which is when I discovered that I don't know get 35 over there. Okay. Should have been about 1.3. Well, you put 1.3 in here now. You're not going to get 17.6. You got 1.3. 1.3 squared is about 1.7. So 1.69 is about 1.7. That's going to give you something here. It's closer, maybe 13 or 14, 12 or 13. And estimate should work out a little better. So I did write out the solution to b to the 4th equals 70 over 25. We raised b to the 4th to the 1/4 power because that raises b to the 4 times 1/4 power. When you raise a power to a power, you multiply the powers. Everybody should understand that and understand that in a way that they can verify it anytime they need. Okay? So anyhow, you do that. B to the 4th to the 1/4 equals 70 over 25 to the 1/4. So B equals 70 over 25 to the 1/4. And that's where I got something that's pretty close to 1.3. Because 1.3 squared is about 1.7, 1.7 squared is a little over 2.8, and 70 over 25 is 2.8. Probably like 1.28 or 1.29. All right. Okay, the process there illustrates how you use an exponential function model. So it's like, okay, I observe my fish population, if it's still a fish population. I observe the fish population, T equals 2 and T equals 6. And then I create an exponential model how to use to extrapolate what my population might be after a year. So now I know how much fish we could buy for a year. That makes sense. That's a very practical thing. Also, of course, growth rate, growth factor, and all that stuff with finance. Very important thing in everybody's life. Most of you aren't going to raise fish, although I'm sure I've inspired at least a couple of them. Fair enough. So this is good stuff. Gives you an overview of the question and gives you a context for the study of exponential functions. And the assignment that was due last night, which most people didn't do, but get done by the end of the week, so you know what's going on. Just gives you a lot of examples of exponential functions and how they apply. Okay. Okay, let's stop for a second. Okay, graph of y, rough graph of y equals 2 to the x, into all the construction and stuff, but we know that it looks something like this. And there's a point there where y equals 4 and x equals 2. And of course, that's a quarter of the box that we usually construct it in. So we should be very familiar with that. Okay. y equals 3 to the x. We've got to go all the way up to y equals 9. And we did this graph. We just low here. But then price is much higher. Y equals 3 to the x. Okay. What about y equals 1/2 to the x? Well, ½ to the -2 gives you 4. And there are the steps to figure it out. Reciprocal 1/2 squared, 1/2 squared is 1/4. Reciprocal 1/4 is 4. Yeah, you should understand that very automatically. But that means that the graph of y equals 1/2 to the x is going to go through this point. 1/2 to the 0 is 1, so it's going to go through this point. And 1/2 squared is 1/4. It's going to go through a point down here. It's pretty close to the x-axis. Now you have this graph that looks like this. And here's y equals 1/2 to the x. Okay. Similarly, you can work it out. Y equals 1/3 of the x is going to come down like this. And you get this kind of neat shaped graph that you're going to see on your homework. Okay. If you understand that much, you'll understand what you're seeing when you encounter it on the section 4.2 homework. Now, there are other things you can do with graphs. What's the graph of y equals 2 to the x plus, oh yeah, but if y equals 1/2 to the x, that could also be written as 2 to the -x. Because of course, 1/2 the negative power, you do the reciprocal thing like we did here. And, you know, so make sure you understand this and understand how these two graphs over here on the left are just reflections through the y-axis of these two graphs on the right. Now that's a process you should be familiar with in regard to the chapter, reflections and transformations and all that stuff. That some people tend to stay shaky on throughout the course. So make sure you get a little less shaky about those things. If you are shaky, some of you are shaky on that. Okay, anyhow, we've got y equals 2 to the x plus 3. So what's that graph going to look like? Okay, let me show you. Not a very good curve. Y equals 2 to the x. Now, doesn't have enough curvature. Not a really great graph. Of course, now we know that y equals 2 is here, y equals 1 is here, so y equals 3, of course, is here. and our red dot here. We want to do y equals 2 to the x plus 3. So f of x equals 2 to the x. This is f of x plus 3. And to the 4, f of x plus a, which means we have a vertical shift of 3 units. Just put it in the context of what we spent a lot of time doing. So you can just visualize it this way. It means you just move that red dot up 3 units. You don't have a vertical stretch. Now we've got a new rectangle. And we subdivide that rectangle and so forth. So you should understand that. Now there are really only 2 of our, well, we usually don't do a horizontal shift of an exponential function, because that doesn't change the shape of it, that just changes the y-intercept. If I move this function over to the left, then the y-intercept is higher. That just changes the number in front. Okay. I just said instead of 40 times 1.23 to the x, for example, if we shift it to the left, we might get 90 times still 1.23 to the x. It doesn't change those factors. So whether you understand that or not, don't usually mess with horizontal shifts. It's exponential function. We could. There usually isn't a reason to. One thing we do is compressions. We'll be talking about that. Horizontal compressions. You've seen it in the homework stuff. We haven't talked a lot about it because it doesn't apply till we get to exponential functions. Okay. Quadratic functions and power functions and polynomials and everything, we usually don't do a horizontal compression. Just like the exponential function, we don't usually do a horizontal shift. Not that we could. Okay. So what you understand then is the plus 3 is just going to take this graph here and move it up 3 units. So I'll throw that into this picture. Here's x equals 1. So well, here's x equals 4. Sitting on very simple scale. Here's x equals 3. That's our y equals 3. Then the 2 to the x curve is just going to come up something like this. I didn't draw that part well, but this curve down here, it's raised 3 units at every point. That makes sense. Then you go back to the box. The box goes up 3 units. The rectangle goes up 3 units. Everything goes up 3. Ouch. I have to round that corner off the floor for myself too. Okay. Where is my chainsaw? Okay, I don't want to use a chainsaw. The thing I want you to see about this curve is it has an asymptote. What asymptote does it have? Okay, well, I just asked everybody to tell me whether we have a horizontal or vertical asymptote of this function. Yeah, just ask them to point this way or this way. Everybody pointed this way, or maybe this one. This one. Okay. So indicated everybody sees that there's a horizontal asymptote. I asked what the equation was. Nobody wanted to tell me. Okay. Okay, well, we're still getting used to the meanings of some of these things. Right? Hopefully we can focus on the meaning of the horizontal line here. Just a few seconds while we did. Okay, so I just raised my hand, told people Tell me when I'm at the horizontal asymptote. Everybody yelled, stop, when I got right there. Okay. And yeah, that's the horizontal asymptote. What's the equation of the horizontal asymptote? I wouldn't want to tell me what the equation was. It's written right there. Okay. How many times have you labeled y equals something? You were labeling the equation of those horizontal lines, the equations. How many times you labeled x equals something? Okay, you were labeling the equations of those vertical lines. Open Math told you that, I told you that. But it's so obvious that you don't really pay any attention to it. Okay? So I'm saying, well, now you gotta pay attention to it. Okay? That's the equation of a line, just like x equals 2 is the equation of this vertical line. Okay? Those are the equations of lines. And again, it's so easy that people neglect it. Okay? Yeah. Doesn't mean you're a horrible person. Just means. Okay. All right. Well, it's important because horizontal asymptotes. You can raise an exponential function or lower it, create a new function with any horizontal asymptote you wish, just by adding or subtracting the number under each equation. Okay. Now there are other things we can do, of course. We can take exponential functions upside down. Okay. Now, how do you get this exponential function from this? If we get this one from the 2 to the x shape, or the 3 to the x shape, we'll go with the 2 to the x shape. So what did we do? We flipped it upside down. How do you flip something upside down? Well, y coordinates that were positive now become negative, right? That means you have y equals negative 2 to the x. Okay? Then you can construct that in a rectangle. Just subdivide the rectangle this end toward the x-axis and use the same vertical lines. Okay. And it's just exactly the same as what you've got here. It's flipped upside down, and you don't really need the rectangle, but it doesn't hurt to use one because it brings you into the context of the picture that I'm trying to get you to carry out in this course. It will help you understand and apply transformations when and if it becomes important for you to do so. Okay, there it is. So if we raise this thing up to, let's say, about here, this is y equals 2 to the x. This rectangle is congruent with this one. Same size, same shape, everything, right? And what's the equation of this one? You have to make an estimate. Remember, it's a 4x4 rectangle. Okay, now, first place, let's take one of this picture. There's a rectangle there, there's y equals negative 2 to the x. A bunch of stuff. So that means you draw every detail. Okay. And when you construct these things, a test construct every detail. If you're not doing all the details, you're missing stuff. Okay. And I can see too much of that with tests. Although most of you have taken the test. Think back to the test we had 2 weeks ago. Well, I asked people to sketch this picture and then sketch the asymptote for this function. And label it. Okay. For the asymptote, I mean, here's what the asymptote looks like. It keeps getting closer and closer to the asymptote, but don't guess that. Okay. Function, be precise, graph the function. So the asymptote is going to be this here. Now you know what the pattern is inside of the constructor rectangle. You keep going twice as close. Well, if you construct like this, you keep going twice as close to the x-axis and moving over one, right? You go to the left, you keep getting twice as close and keep moving over one to the left. And you keep that up forever, you never get to the x-axis. There's always a little bit of distance left to go halfway, and that still leaves you a little bit of distance. It gets really tiny. Okay, it gets invisible almost. Well, it does get invisible, but it's still there. Something you really have to understand about exponential functions. Okay, well, now you just have to label this. This is a horizontal line. It's y equals what? Well, you know, if you have an exact or a reasonable sketch, there's a gap between the x-axis and this little line here, right? And this thing is 4 units high. So some people estimated y was 3. And that would be if this thing was a little bit lower, that overlap down here. That's okay. I wanted to see where the asymptote was and see that it's a y something. Okay. So I'm going to estimate something nobody has. I'm going to say it's about y plus 5. To stretch 4, that looks like about 1. Okay. If you have y plus 3 or y plus 6, that's fine. The way you drew it, that might be a good estimate. Okay. Yeah, it's probably a little over 5. Yeah, it's a little more than a fourth. It's not half. It's 5 or 6. So I could take 5 or 6. 3, you missed a little detail, but that's not important for what we're trying to do right now. Okay. But again, draw the whole picture and do what you can with it. Okay. So now we can say that, on your paper, now tell me what the equation of this thing. Wait. Assuming it's a good exponential curve. My estimate for the asymptote is 5. This would be y equals negative 2 to the x plus 5. Top of the box was on the x-axis here. Top of the box is on y plus 5 here. That means the whole box has been raised up 5 units. How do you raise? If you have a box, a window, we call this a window on the function. If that window raises up 5 units, you got to add 5 to all your y coordinates. So that the x-axis, which is y equals 0, will become y equals 5. The slope but then you get this function, this 5 units high, is this. Now, you want to really understand what we've been doing since the beginning of the course with moving these boxes around and doing the AF and X plus H stuff. Okay? Because it's just a fairly simple example of that. So all we're doing is just a vertical shift. No horizontal shift. Confusion. And of course, I don't get vertical stretches. You can really scan through your upcoming homework. Make sure I'm touching on the things that will help you understand what you see. Uh, Shift this thing 1 unit to the left, just a little. Sure. So you start out with your exponential function in the note. Make it a 4x4 window. Symmetric about the y-axis is sitting on the x-axis. That's our basic construction. Then we move this 1 unit to the left. Well, the reason to do that, just take the box, here's your x equals 1, line. So everything moves over this way, and the function goes here up to here. Look like that, is it? Okay, well, what's the equation? What's the equation of that line or that curve? Up next, it comes up of x minus h. Right? Now again, go back to look at how we were shifting these things almost from the very beginning, okay? And look at what you missed. Just an example now. Look at what you missed. I've got to do it all the time because I'm reading a fairly rigorous treatment of Einstein's general theory of relativity. Did a lot of stuff that I never had a chance to do back when my brain worked. Okay, so I'm just trying to see if what's left of my brain can comprehend it, not getting it at a certain level. I'm not going to be ready to do research in gravitation. It takes more horsepower than I've got, but I am getting to the point where I'm understanding geodesics and four dimensions, space time and stuff like that. But I've been reading this book by Leonard Susskind, part of his theoretical minimum series. I guess I've read some parts of that book a dozen times. And every time I read it, I see something that I should have seen the first time. Okay. Well, the analogy is there's a lot of stuff you should have seen with the early stuff we did in this course that comes together at this point. And if you understood it there, then you're going to be pretty good here. If you sort of kind of understood it, well, you're going to struggle a little bit here, but it should come back to it. Okay. So you might want to go back and look at some of the problems. You know, I mean, problems on the test. Let's say, you know, you get the reciprocal function, you move the red dot here. Okay. Now what's your new function? Okay, people were able to do that, but that's exactly the same thing that we're doing here, but you might not recognize it. Understand what I'm saying? So go back to how we did that, because of course it's on the midterm. Okay. Not necessarily the reciprocal function, but we have that problem. I warned you about that. Okay. First problem, the last problem on the first test will appear on the midterm. Different functions, different format, different numbers. But those are really key problems, and they're going to appear on the final too. So you want to get those down because it's easy points. It's a 40-point problem on the first test. Okay, it's worth 40% of your grade. Okay, then you have that last problem. It could have been worth 10 or 20 points. It's an indication. Those are kind of touchstones. Okay, so you want to put all that together and understand this in the context of what we did there and what you were doing. If you're just doing it mechanically by memory without thinking about it, well, that's how you learn. That's a stage in the learning process, and it's a good stage, but you want to get to the end of that stage, okay? You want to understand it. Okay, so horizontal shift becomes this. F becomes this. So just a hint that I'm giving this a lot of emphasis. Okay. Make sure you understand that statement. Now, the other thing is, what does that do to the graph? It's still got the shape of an exponential. The only thing that changed was its y-intercept. Okay. So this function has a y-intercept of 0 to 1. This one has a y-intercept. Well, what is the y-intercept? It went higher, didn't it? Oh, if you put in 0 for x, you're going to get 2, aren't you? Another thing you need to understand about exponents is going to be important at some point. Even the x plus 1 is 2 to the x times 2 to the 1. Because of rules of exponents that you really have to understand. As I commented in my previous class, I'm not going to teach you the laws of exponents. I'm going to tell you to learn. Now, I'm not ordering you to learn them. We're not going to be thrown in prison if you don't. But you're going to pay a big price on this chapter if you don't thoroughly understand rules of exponents. And if you go on to a subsequent math course, you're going to continue paying that price. Okay? If you have especially a calculus course or a pre-calculus 2 course, you have to understand the rules for exponents, and they have to be second nature to you. So I recommend you do 100 problems every day until they are, or once a week. Typical problem with the rules of exponents takes about 30 seconds. We spend an hour to do 100 problems. Okay. I'm not saying literally that you should do that. And if you want problems, I think I've got a bank that has millions of problems. Okay. I think I've generated, I mean, it'll generate millions of problems in just a couple of minutes. Less than that, just a few seconds. So I can probably locate that. One copy, so you can just add. Might even post one if I can find it easily, but I'll be great to test. So, all right. Okay, let me take another look. I'm trying to confine most of this to what you need directly for homework, which is to understand these shapes and when they're shifted and so forth in the transformations, because you're going to ask, you're going to have questions on it. And hopefully you can answer those questions without having to look at a very similar example. Because it's when you can answer the question without help of a video or an example that you pull it out of your memory in such a way that it's going to stick. Okay. I mean, it's already stuck. If you pull it out of your memory, it's that much better every time you pull it out of your memory. Okay. So when you do these problems, make sure you understand as much as possible about what you're doing related and everything else you're talking about. Okay. Take a quick look. I don't think I've left anything out, but every time I think that, I have. Just a comment. Now, should be pretty obvious. For this function here, the yellow one, as x goes to infinity, what does this do? Does it go to infinity? Does it go to negative infinity? Or does it approach something? As x goes to infinity, that means you go, or you want that way. What happens to y? Goes to infinity, doesn't it? Okay. Now that's a language that you've had because you used it a lot in the previous chapter when you were talking about polynomials and long run behavior, right? Sometimes the long run behavior went to infinity, sometimes it went to negative infinity, sometimes it approached a straight line slant asymptote, sometimes it approached a horizontal asymptote. Sometimes it approached a specific number, which would have been a horizontal asymptote. Okay. So as x goes to negative infinity, what does this do? Can you show me with your fingers or arrows or whatever? It keeps approaching the line y equals 3, so it approaches 3. As x goes to negative infinity, this thing approaches 3. As x goes to positive infinity, what does this thing approach? You can show me positive infinity, you can show me a negative infinity, you can show me a number. 5. Okay. What about this one? X goes to infinity. And you can answer it for the white or the yellow, and the answer is going to be the same. Okay. As x goes to infinity, what happens? Goes to infinity, good. Okay. As x goes to negative infinity, what happens? Yeah, some of you are shaking a fist. I think you mean to. Okay, I don't blame you for shaking the fist. It's perfectly valid. Just watch out, I can defend myself a little bit. Okay. Not enough. All right, we'll leave it at that.